LangChain, probably one of the hottest things in AI right now after vector databases. It's a framework used to develop applications on top of large language models like GPT, Llama, HuggingFace models, and much more. It first started as a Python package, but there's also a TypeScript port catching up in feature parity and a Ruby one that just got started. But why is it needed in the first place? Couldn't we simply send a request an API or model and call it a day? And you're right, that would work for simple applications, but as soon as you start increasing the complexity, like connecting the language model to your own data from Google Analytics, Stripe, SQL, PDF, CSVs, or making the language models take actions such as sending emails, searching the web, or running code in your terminal, things start to get messy and repetitive. LangChain offers to fix this issue with components. We can use document loaders to load data from sources like PDF, Stripe, and then optionally use a text splitter to chunk it down before storing it in a vector database. At runtime, the data can be injected in a prompt template to be then sent as input to the models. We might also use tools to take actions, for example, sending an email with the output's content. In practice, these abstractions mean you can easily swap to another LLM because of cost or features, test another vector database capabilities, or ingest another data source in a few lines of code. Chains are how the magic happens. We chain together components in a way to accomplish a specific task. Agents are more abstract. They first think about what they need to do using a language model before doing it, using things like tools. If you're curious about research papers showing the power of connecting language models to your own data and the outside world, consider looking at Self-Ask with Search and React, which were published around the same time LangChain was launched. Now let's take a look at what's really going on behind the scenes. There are currently 7 modules LangChain offers that newcomers to the space should know about: models, prompts, indexes, memory, chains, and agents. Models. At a high level, there are 2 different types of models: language models and text embedding models. The embedding models turn text into an array of numbers. We can then think of text in a vector space. In this image, we can see how in a 2D space, man is the king, what woman is the queen. They represent different things, but we can see a pattern. This allows for semantic search, where we look for pieces of text that are most similar in meaning for a given piece of text within the vector space. For example, OpenAI's text embedding model can embed large pieces of text, precisely 8191 tokens, which, given their word to token ratio of 0.75, should roughly work for up to 6143 words. It outputs vectors of 1536 dimensions. We can use LangChain to interface with multiple embedding providers. Some APIs like OpenAI and Cohere are paid, but we can do it for free and ensure privacy on our data by using open source models run locally. With HuggingFace's open source embedding, you can now create your own embeddings on your own machine using only 4 lines of code. However, the number of dimensions might be different and the quality of embeddings might be lower, which could make retrieval less accurate. Moving on to language models, there are 2 different subtypes: LLMs and chat models. LLMs wrap APIs which take text in and return text. Chat models wrap models which take chat messages in and return a chat message. It's a subtle difference, but the interface to use them is the same. We can import both classes, instantiate them, and then use the predict function on both of them and see the difference. However, you probably won't be passing text directly to the models and instead use prompts. A prompt refers to the input of the model. We often want more flexibility than in hard-coded string. LangChain provides the prompt template class to construct a prompt using multiple values. The important concepts to know of prompts are prompt templates, output parsers, example selectors, and chat prompt templates. Prompt templates. Here's an example. First, you want to create a prompt template object. There are 2 ways to do this. Import prompt template, then instantiate one using the constructor. Specify your input variables in an array and in your template string by putting them inside of curly braces. If you're feeling lazy, you can also use the helper method from template, so you don't have to specify the input variables explicitly. In both cases, you can then format the prompt by telling it what values to replace the placeholders with. Under the hood, it uses f-strings to format your prompt by default, but you could also use Jinja too. But then why not just use f-strings directly? The prompts help with readability, play well with the rest of the ecosystem, and support common use cases like few-shot learning or output parsing. Few-shot learning means we give our prompts a few examples to guide its output. Let's see how this is done. First, create a list with a few examples. Next, we specify the template to format the examples we have provided. Every example will be formatted using this prompt template. Finally, we create the few-shot prompt template object. Pass in the examples, the example formatter, a prefix given the command, and suffix that aims to guide the output of the LLM. Let's not forget the input variables and a separator that will be used to separate the examples from the prefix and the suffix. We can now generate a prompt, and this is what it looks like. This is an extremely useful paradigm to control the output of the LLM and guide its response. Similarly, we might want to use output parsers. We will be automatically parsing the output of the language model into an object. It's a little more complex, but very useful in structuring the random outputs from LLMs. Let's say we want to use OpenAI to create joke objects. We can define our joke class. To be more specific, we'll need the joke's setup and punchline. We'll add descriptions to help the language model understand what those mean. Then we can set up a parser and tell it to parse using our joke class. We use the Pydantic output parser, which is the strongest and most recommended. Now we create our prompt template. Let's pass the template string, input variable, and we can use the partial variables field to inject our parsing instructions into the prompt template. We can then ask the LLM to tell us a joke. Now that we have our prompt ready, this is what we need to do to send it to OpenAI. We'll first load our OpenAI API key from our .env file, then instantiate the model, run its call dunder method, and parse the model's output using the parser that we've instantiated. And there we go. We now have our joke object with its setup and punchline defined. The generated prompt is pretty complex. Consider checking out the GitHub repo to have a better look at it and to really understand what's going on. We've previously covered few-shot learning, where we pass along examples to show the model expected answers for a certain type of query. It might be possible that we have many such examples and we can't possibly fit all of them. Also, that could become pretty expensive pretty fast. That's where example selectors come into play.
To keep the cost of a prompt relatively constant, we'll use the length-based example selector.
Just like before, we specify an example prompt. This defines how each example will be formatted. We create our selector, pass in the examples, and then the max length. By default, the length refers to the number of words and new lines used by the formatter example section of the prompt. And we can take the previous few-shot template we defined and simply add the selector we just created, replacing the example keyword argument. But what about interacting with chat models? This brings us to chat prompt template. As we've previously mentioned, chat models take a list of chat messages as input. The list is referred to as a prompt. What's different about them is that each message is prepended by a role, either AI, human, or system. The model is supposed to follow instructions from the system message closely. There's only one system message at the beginning, and it can at times sound pretty hypnotic. You are a kind customer service agent, responds diligently to the customer's question, ... Something like that to tell the chatbot how to behave. AI messages are messages that come from the model. Human message is what we've typed in. The roles give the LLM better context on the ongoing conversation. Models and prompts are cool and standardized, but how can we use our own data? This is where the indexes module comes in handy. Data is the new oil, and you can definitely dig anywhere and find tons of it. LangChain delivers the rigs by providing document loaders. Document is their fancy way of saying text. There are a ton of supported formats and services like CSV, email, SQL, Discord, AWS S3, PDF, the list goes on and on. It can take only 3 lines of code to import your data. Here's how easy it is. First, import the loader, then specify the file path, and then call the load method. This will load the PDF as text in memory as an array where each index represents a page. That's nice, but when we want to construct a prompt and include text from these pages, they might be too big to fit within the input token size we've talked about earlier, which is why we'll want to use text splitters to chop them into chunks. After reading the text, we can instantiate a recursive character text splitter and specify a chunk size and a chunk overlap. We call the create documents method and place our text as argument. We then get an array of documents. Now that we have text chunks, we'll want to embed and store them to eventually retrieve them using Semantic Search, which is why we have Vectorstores. This part of the indexes module offers multiple integrations with vector databases like Pinecone, Redis, Supabase, Chroma DB, and much more. Once you have your documents ready, you'll want to choose your embedding provider and store the documents using a vector database helper method. Now we can write a question and do a similarity search over the vector space. Moving on to the retriever part of the module, the retriever LangChain has the most support for is the Vectorstore retriever, which you can get by calling as retriever on a vector store. Note that the retriever interface is generic and doesn't have to represent a vector store. It could also be querying services like Wikipedia, a ChatGPT plugin, or a couple other integrations. It only has to implement the get relevant documents, which takes in a string and return documents. As an illustrative example, one thing you could do is self-querying with Chroma. Say you have films stored in Chroma DB. The movies have as metadata score and genre. Then you could run the following line of code and get the movies that you wanted. Now that we have models, prompts, and indexes, we can use chains to abstract a model call to an LLM. We can instantiate our model, write our prompt, and then pass our model and prompt to the LLM chain. We can then run the chain on the input variables of our prompt. The chain takes care of formatting the prompt, sending it to the model, and returning the results. This is a stateless operation, meaning the chain does not remember previous interactions. We could use memory to make it stateful. Let's instantiate a chat model and now use a conversation chain. We'll pass the chat model along with a memory object. Now we'll ask it to respond partially to a question, and then to complete its answer. You could also create your own custom chains, or use high-level chains to do things like chaining chains together, solve math problems, or even things like letting the LLM write code and then execute it. Let's say we want to create a company name and write a good catchphrase for it. We can chain both LLM calls in a chain. After instantiating our model, we create our first prompt and our first chain. Then we write our second prompt asking for the catchphrase and create our second chain. Now we can chain them using the simple sequential chain and specifying the chains in order. We run the chain on the input variables of the first prompt, and its output will be used as input variable for the second prompt. There are also a couple of pre-made chains that you could use, like the LLM math chain. Moving on to agents, as this video is already getting pretty long, we will cover agents more in depth with real-life examples, concepts, and working code in a following video. This is a hot space and has tons of practical applications. If you want to be notified, hit the subscribe button, and as always, thank you for watching.